a rubber block sits on asphalt. Coefficient of friction apparently for rubber on asphalt, I'll go for the bigger, let's say 0.8. And has a mass of, I don't know, what's a typical tyre? What's the mass of a typical tyre? 15 kgs, 20 kgs? 25. Yeah, it can be a tractor tyre. If that number's rubbish, then it's a tractor tyre. They're way more than that, aren't they? Yeah, okay, so it's got a mass of 25 kgs. What force pulling up at an angle of 40 degrees is required to move it along, or technically to keep moving it once it's already moving, so to have zero acceleration. So this is a type of question which could sneak into the exam. It's a flat surface with an inclined force, and we're allowed that legitimately. And I would say to you, if you ever get to do one of these, draw a picture. As soon as you draw a picture, it starts to make sense. So here's our asphalt surface. Here's our block, which may be round if it's a tyre, but it's a block. It's been pulled up, so we've got a string on it, which we're pulling up. So you've got some person here, and string over the shoulder, pulling the block. So it's been pulled up at an angle. That's irrelevant, and you don't need my crappy drawing of people, but you get the idea. So it's been pulled up at an angle of 40 degrees. That's the pull at an angle of 40 degrees. Right, same as I did last time. Which other forces do you want me to put on this diagram? What other forces do I need on this thing? Gravity, okay? So we've got, which the same as usual is going straight down. Okay, so the weight is, Harrison's already pushed the button so he can tell me, it's 25 times 9.81, 245.3 for one decimal place. 245.3 newtons is the weight going down. Brilliant, okay, loving that. What other forces do you want me to put on this? In, okay, which always acts at right angles to the surface, so that's pushing back up. So it's got a normal force pushing up. Yep, agree with that. What else? One more. Friction, thank you, Ricky. It had to be there, didn't it? So if it's trying to move it this way, then friction is coming back that way. Rightio. What's the drama with trying to make those forces do things? The 40 degrees? Yep. So on the last one we did, we said that N was equal to W, which isn't the case here because this P is going to stuff it up. The sum of P is basically helping N. So N will be less than W because N plus this bit of P have to equal W. So if we think of P as having a bit that goes up and a bit that goes along, and I'm resolving these perpendicular and parallel to the surface. It just happens in this case that because the surface is flat, they're also horizontal and vertical. But in my head, I'm doing this one at right angles to the surface and this one across the surface. Yep. Okay, so if that's 40 degrees, look at the, I could have drawn it that way, shouldn't I? So So this is also 40 degrees. So this one is opposite. So this thing over here is P sine 40 degrees. And this one is adjacent. So it's P cosine 40 degrees. Yep. So far, so good. We've drawn a picture. We've sorted things out in terms of perpendicular and parallel. And now we can write two equations. So what's going on in this direction is that the force of friction pushing it to the left is exactly the same as P cos 40 degrees coming back this way. And in the up and down or perpendicular thing, we've got up is N plus P sine 40 degrees has to equal whatever's going down, W, which we've got a number for. No, N plus P sine 40. So upward force plus upward force is equal to downward force. Yep. And out of this, somehow, we're supposed to be able to get P. We're trying to get P out of all of this. The other bit of information we haven't used is this one. Yep. So we know that mu, which is FF over N, equals 0.8. Okay, so here we go. So 0.8 equals FF P cos 40 degrees divided by N. So N is just W minus P sine 40 degrees. Yeah? So from here, I can rearrange this one. N is W minus P sine 40. So I've got an expression for FF. I've got an expression for N. I can stick them both into there. And now I've got an equation. The only thing I don't know is P. I've got a number for W. Yep, I've got a number for W. 40s are just numbers. I'm not scared of those. That's a number. We should be in. So a little bit of rearranging to get P by itself, and we should be able to do it. So let's pop that up on that side. So we get 0.8 W minus 0.8 P sine 40 equals P cos 40. Let's get both the P's on the same side. So 0.8 W equals 0.8 P sine 40 plus P cos 40. Factor a P out the front and do a division. So 0.8 W divided by 0.8 sine 40 plus cos 40. W I've got a number for. And all I have to do now is push some buttons on the calculator. And while you guys are all frantically busy copying that down, I'm going to steal Harrison's calculator and do it. So what have we got? 0.8 times 245.3 divided by 0.8 times, let's make sure this thing's in radian or degrees, 0.8 times sine of 40 plus cosine of 40 equals 153.3. Thank you, Harrison. I trust that that's the right calculation. It looks like a reasonable sort of number. Okay, so the weight of the block is 245 newtons. So to drag it, we only need 153 newtons compared to the 245 newtons. If we dragged it just flat, we'd have needed 245 times 0.8, which is what, about 190, pushing 200. So pulling on an angle means we need less force than if we just pull it flat. Okay. Looks kind of mathy, looks kind of entertaining, is kind of entertaining. But the trick is you definitely need one equation for parallel, you need one equation for perpendicular, and then you've got the ability through this formula to join those two together. And that'll leave you with one thing you don't know, and you can work out what the pull force in this case is to move it along. Any questions about that one? Comments? Or? There was one exam question once that was pretty much that. It's worth a few marks, but it's good question. So call that one friction with a pull at an angle. I'm going to just change the question just a little bit, and then I'm going to let you have a go at working it out while I go and print out some notes. If you want to have a bit of a break, if you need to go and get a drink or something, now would be a good time to go and do that as well. But all I'm going to do, I'm going to change the question by going exactly the same question. Okay, so instead of pulling on a rope and trying to pull it up, you're now trying to push it along, but you're pushing down on an angle. So the only thing that's going to change, well, I'll rub out all the other rubbish. Okay, so rub out all that stuff, it's all going to... The weight's exactly the same, but now instead of pulling up that way, you're pushing down that way. Okay, that's the only difference. And the question is, what difference does that make to the force that you have to apply to the thing? Okay, so have a play around with that one and see how you go. So the first thing's clearly going to be that friction's now going the other way, isn't it? So we're trying to move the block this way now, so friction's going to be going that way. Okay, that's the bits, that's all the forces. Have a play around with that and see what you come up with. Take a break on the camera. We're going to call this one friction pushing down.